face the beaker. In order to wipe off the electrode like this, make sure to blot it so we don't damage the actual sensor at the bottom. So if you want to come close, you're going to take the first buffer solution, which is 7. You're going to take the electrode and swirl it into the meter. If you look at the pH meter, we swirl it.
Okay, so we're using the 2-point calibration method. When testing for an acid solution, we're going to use the buffer 4 to bring it down to about 4 with a range of 0.05. So we take it out of the distilled water and we blot the electrode so as not to scratch it or bite it. And then we place it in the buffer 4 solution and we're going to swirl it, taking care not to hit the sides of the beaker. And we're going to read the meter till it gets to about 4. We're done. We're going to clean it off in a separate beaker with distilled water. And place it in the distilled water before we...
Alright, so now I'm going to take the pH reading for this unknown. Step closer. Wait for it to stop. But it looks like it stopped at 4.14, so the pH reading shows that it's an acid. Clean it back off.
Okay, we're doing a 2-point calibration for the pH meter. And what we have to do is pretty much dry the outside and make sure you blot the inside. You want to blot the inside so you do not destroy the sensitive electrode meter. And once you do that, then you want to go ahead and rinse this off. This is set. Nice rinse. Rinse it off again. You want to blot it, not destroying the meter, because if you destroy it, you destroy your experiment. You don't want to do that, because then you'll have to do it all over again. Alright, I'm going to actually use the pH buffer 7. And we do this if we want to get the pH calculations for the bases. Alright. And what you do is you go over here and you swirl it, swirl it, swirl, swirl, swirl. We're going to go ahead and take a look at this meter. And as I'm swirling it, you see that it's constantly going up. We want it to actually get to a 7. We can have, error plus or minus 0.05, which is fine. That's in the range. That's what we want. That's ideal range. Okay, we have to wait till it stabilizes. Still got a while to go. This process can be tedious at times because it takes a while for things to stabilize. Science. That's science for you. Yes. As you can see, been here already for 30 seconds and it's taken a while. All right. Woo, we finally got it to 7. It's stabilized. That's what we need. After we go ahead and get our pH of 7, which is great, you want to go ahead and rinse it off again with the distilled water, or aka deionized water. Once you do that, you're going to go ahead and plot the electrode as such. And when you're not using it, you want to place it in here in distilled water. That way, it won't mess up your calculations in your experiment. Thank you. For a strong acid like HCl, will completely ionize in the solution. As I have a diagram here, this is the solution, it deionized. You don't see anything. Whereas in a weak acid like acetic acid, when it goes into a solution, it partially disassociates. And for your strong acid, you have HCl, which is a forward reaction, and it breaks down to H plus and plus CHL minus. Whereas in the weak acid, you will actually have an equilibrium. You will have a forward and reverse reaction. 3COO minus plus the H plus. And your equilibrium constant will look such as this. The reason why solids and liquids are not included in an equilibrium constant is because the solid and liquids, their concentration equals 1. As I have an example of that, you have 2A solid, 2B which is aqueous, your equilibrium, you have your C, liquid, and your 3D as an aqueous. Here, we write the concentration constant, you have your C to the power 1, D, 3, A2, B2. Come over here, because it's a liquid and a solid, it's going to just be 1, 1, so they cancel each other out, leaving D3, B2. And that's the reason why solids and liquids are not included in the equilibrium constant.